So with that, I am going to turn it over to Matt.
Okay, can you see my slides?
I can.
Okay, good. Thank you everyone for taking your precious time to come to this talk. My name is Dr. Matt Moynihan, and I'm a nuclear fusion expert. I've been in the space a long time. But what I'm talking about today is sort of out of necessity. It's superconductors, because essentially the field of fusion and the field of superconductivity are colliding. Most fusion concepts require a big bad magnet to work, and superconductivity is being accelerated by fusion companies. And the question is, what can the US military, specifically the Navy, get out of all of this? What practical things can we extract? So that's what the talk is going to be about. Feel free to stop at any point if you have questions, okay? I'm showing two images here. On the left is the all-electric ship, the Zumwalt. And the all-electric ship is a really impressive Navy platform because the commander on the ship has the ability to move power electrically around the ship for different combat scenarios. So if he has to run away from the bad guys, he can transfer power to the propeller and get away. If he has to stand and fight, he can move power to the weapon systems and fire back. Now, he can do that because of a $22 billion, 30-year development program within the Navy around an all-electric ship. All-electric ships are more efficient at using power, and that's why the Navy went in that direction. They developed hardware, software, diagnostics, and they even attempted superconductivity to develop for this ship. So that's what's on the left. What's on the right is a stellarator concept from the startup Thea Energy. And if you know anything about stellarators, you know that they're the best fusion machine from a plasma physics perspective, but they're incredibly hard to build. So there's a host of companies in that space, and every startup is trying to come up with an innovative, lower cost, simpler way to build the stellarator. And so Thea came out of Princeton a few years ago with this idea that they could make a stellarator by coating the surface with thousands and thousands of these little point magnets that could reconstruct the twisted field of the stellarator by adding together all their magnetic fields. As part of this, they're going to control power to these magnets because they're going to be electromagnets using artificial intelligence and diagnostics. So they have a system that has hardware, software, diagnostics, and superconductors to manipulate power on this fusion reactor. The same thing comes in the Zumwalt. So what I'm saying here is that fusion is tackling many problems that the Navy also faces. The Navy should be looking at fusion for innovations to pull out of there for technology transfer. And the Navy should have a vested interest in the US private fusion industry. All right, so I'm going to give you a little bit of history of me, who I am, the background really for the talk. Then I'm going to talk about the innovations that are coming out of fusion for superconductivity. There's a whole basket of technologies, and Michael's really going to talk about this more in his talk. So I'll kind of let Michael fill in the blank here, but there's a whole number of things that are happening in fusion for superconductors, and they really haven't rippled into the wire, the motors, the generators, the energy storage systems. And so where superconductivity is now with the limitations is going to change as these innovations from fusion startups ripple into the rest of the supply chain. I'm going to switch perspectives and talk about the Navy's history with superconductors and the integration challenges that the Navy has already sort of seen and identified with this technology, because you don't get the technology for free. I'm going to talk about the application space, which is really wide open, and I just want to let you guys sort of fill that in, because I know what the technology sort of is, but how we use it is really up to you folks. And we'll talk about some next steps, okay? Feel free to interrupt at any point if you have questions. This picture here is from a few years ago. This is wire that was supplied to Commonwealth for their big 20 Tesla magnet. And I believe it's super ox wire. This wire is compared to number 10 wire from Home Depot that I bought. These two are electrically equivalent. You can pack as much current in all these cables as you can in this little thin wire on the left. And the comparison, the notes on the comparison is down here. It's 750 amps per square millimeter, and copper wire is anything from 30 to 40 amps for a number 10 gauge wire. So as I said, I'm a nuclear fusion expert, 17 years in the field. I've written a book, and I've also worked in the defense world. I was a nuclear engineer at Bettis. I know Bettis is on the call here somewhere. I've worked in the SBIR world a little bit on radios, so I have some radio frequency exposure. And I was just most recently a deputy PM on a Missile Defense Agency project related to directed energy. But my real knowledge set is fusion. That's my core skill set. So if folks are interested to talk about fusion, I'd be happy to come back. Eugene, we can set up another call and I can talk exclusively about fusion because it's a really exciting space. But I got into this topic out of necessity because, as I said, fusion and superconductors are colliding. The fields are tightly linked together, and they will be for the next 10 to 15 years. Most fusion companies cannot make net power without really high magnetic fields. And because of that, they're doing a lot of innovation in the superconducting world that they never had the money to do before. And that's the exciting thing. But again, what should the Navy pull from all this that's practical? All right, so let's look at the innovations in fusion themselves. This on the right is a series of images from Tokamak Energy, who they're going to present later, about their different magnets that they designed through time. And each one of these was sort of a stair step where they went up in field and got better at the technology to the point where they had a 19 Tesla magnet in 2019. And I believe they have gone beyond that since then. But as part of this, the company has patented over 200 patents, most of which are around HTS for a variety of problems, from quench protection to insulation to quench initiation systems to joining tapes and a variety of other things. So these coils are high temperature superconductors, which means they can operate with nitrogen. They have, as part of this, a whole software package for magnet design. They allow for current sharing between wires and between joints. They have built-in coolant channels and built-in quench protection. So collectively, this is a basket of innovations that represent the next generation for superconductors. And as I said earlier, they haven't rippled out of fusion into the rest of the defense industry. So it's really not clear how much better this superconducting technology will be when all these innovations leave fusion startups and make their way into other defense programs. And I'm not going to talk about this anymore because Michael really is the expert here, and you want to talk to him after my presentation. This is the approximate limits to superconductors right now. And I say approximate because all these limits are they depend on a variety of other factors. For example, if you have a 1 kilometer cable, you can get about 200 megavolts out of that cable. Now you can make the cable longer, but you'll have to lose some voltage. You can make the cable shorter and you'll gain some voltage. So that's sort of a rule of thumb. So as a rule of thumb, you're looking at a kilometer cable. You're looking at a motor and a generator that's about a quarter of the volume in size for a normal versus a superconducting generator or motor. A wire, I said 750 amps per square millimeter. There's a huge range there depending on a variety of factors from coolant to temperature, et cetera. For the Commonwealth wire, it was from 500 to 2,000 amps per square millimeter. For energy storage, the SMES concepts, 25 Tesla holds about 250 megajoules of energy in a square meter. So that's a good rule of thumb. Cryogens are still required, hydrogen, helium, nitrogen, but always it's preferred to go to the colder temperatures. So then materials, these superconductors use less rare earth than a comparable permanent magnet. which makes sense because if you want to make the same field with a set of permanent magnets, you need a lot more rare earths. And then the cost is probably the most exciting thing, probably the biggest point. Up until now, cost has been a huge barrier to entry for this technology. But what's happened in the last few years is that the fusion industry is hungry for wire and putting out demand signals that the market is responding to. Most people on the call know that in 2021, SuperOx had a breakthrough in manufacturing the wire, a breakthrough that is now trying to be duplicated by other US suppliers, including Maddox, HITS, and other suppliers. So if you look at the wire price from 2021 going forward, the trend has been about a 25% decrease in wire price every 2 years or so, driven by fusion demand for wire. And if that trend continues, we're looking at a competitive product near towards the end of the decade. So that's the kind of thinking that needs to happen now. If the wire price comes down, many applications suddenly become economical. And so we can start planning for that now. And that's one reason why this should be a topic of interest for all the folks on this call. All right, so I want to switch perspectives and look at the Navy's history with this because there's a long established history. And I am
Hold on.
Go on.
Hold on a second, Matt. Tony,
Yeah.
Tony Bruno, did you have a call or a question? I can't see your whole name.
No, I didn't, but I have seen some of these slides in the past. So we're very interested in what's going on.
And you're with?
Thank you. I'm with Newark in Newport, Rhode Island.
Okay.
I wouldn't have stopped the talk for this question, but since we're at a pause, I'm curious. You gave the number 25 Tesla. That's over half the world record for a man-made magnetic field. Is there a reason you picked that specific number? Is that a target goal, or is that achieved, done something day in, day out?
So field strengths there's a whole spectrum, right? Fusion reactors are generally 3 Tesla when they're made with copper coils, okay? Tokamak Energy did 5, 7, 9, 13, up to 19 Tesla with a field with a magnet about the size of a Frisbee, okay, in 2019. That record was pretty big deal until Tokamak broke it a year and a half later with their 20 Tesla large 6-foot magnet coil. National High Magnetic Field Lab has a coil that can go to 45 Tesla, and the Chinese just broke that record in the fall, or in about August of last year. So they now have the world record for a steady state coil, 45.2 something Tesla. Mm-hmm. But to get to that field, it takes days because it's a hybrid magnet and you've got to feed in current very slowly so you don't heat up the coils. So I think the question is, will all these breakthroughs from fusion make achieving that field reasonable? And I don't know the answer to that question, but I'm going to hazard that because all the companies many of the companies need high fields to make their fusion machines work. They're all going to be looking for that region. Tokamaks, power is predicted between about 10 and 13 Tesla. And that was the design basis for ITER and Spark. So 25 Tesla is probably a reach for a fusion reactor, but 45 is possible with these steady state fields. So that's why I picked that number. It was sort of a guess in a range with all these other competing pieces of information. Make sense?
Okay, thank you. Yes, thank you.
Okay. Any other questions?
Anyone?
Yeah.
I just want to let you know Tom Painter just joined. So
hello, everyone.
Yeah, Tom is definitely going to know more about this stuff than I am. Tom is a superconducting expert from Florida State. So I may defer to Tom if there are real technical questions.
Yeah, thank you. I'm sorry I missed the first part of your talk.
Oh, it's okay.
Glad you're here, Tom.
Thanks.
All right, Matt, go ahead.
Okay, so again, these are performance limitations, and they will probably change as fusion drives this technology forward.
So Matt, is there a formula for currently, like, just like an engine, there is a specific, you can only achieve 40% or 60% efficiency with, is there a maximum based on a formula? Or can you reach 90% or whatever?
I don't think there's a clear answer to your question
Okay.
in terms of so when I review the literature, and again, I've reviewed some papers, I don't have a crystal ball, so there's probably infinitely more papers to read. Motors and generator design studies have been done at a lot of different universities and organizations. And what I've noticed in just reviewing the literature that I've reviewed is that there isn't a universal agreed upon design for the best rotating superconducting system. And on top of that, there's all those other design characteristics that are being put into these fusion magnets that could ripple into the motor and generator. Now, with a caveat that there are different magnet types. There's fast ramp, there's steady state, and then there's a third type that may not be applicable to a motor and generator system. There is a long history with the Navy and superconductivity, and most of it is, I'm sure, classified. I don't have a clearance right now. This is an open forum. So what I pulled was from publicly available sources. For those in the military that have clearances or have the ability to see restricted information, reach out to the folks at the Office of Naval Research, specifically Scott Coombe or Peter Ferrara at the NWSC Applied Superconductivity Office. This picture is pulled from Peter's public talk, and it shows a variety of demonstration and experimental platforms through the years with superconductors. So fundamental research from the 50s to 86 was conducted, and they did 2 motor systems. And then in 86, Rebco was discovered, and there was a wave of excitement. And so that spurred a whole series of minesweepers, a minesweeper program in the 90s, a 5 megawatt generator at Florida State, which Tom probably knows more about. And then those lessons learned were translated to a 36 megawatt ship motor at NWSC Philadelphia in the early 2000s. Then there was a degaussing exploration that was done, and degaussing is essentially a long cable, and that's going to be the first sort of deployment of this technology on a Navy platform. And so now they're also looking at energy storage. That's SMES systems, which is not a new concept. A SMES system is essentially a donut of superconducting wire where you put in current. The current goes around the zero resistant coils, and you isolate the system, and the field allows the current to continue. So essentially you can store energy in these units. So you can think of a SMES system like a giant capacitor, basically, with a magnetic field around it. And what's great about it is when you reattach the system, you can pull energy out with a very high efficiency, greater than 90%, energy in, energy out. So that's an energy storage unit that could go on a ship or carrier, and it could be applied to supply power to a directed energy weapon, a laser, etc. And also you can look at completely superconducting ships, and where the entire electrical grid is superconducting. And there's been a lot of work in the electric ship program specifically on that. There's even a piece of software that was developed called S3D, or Ship 3D, where they can model an entire ship design where you switch to superconducting systems and you look at what the design space for a ship is with that kind of technology. Some things that they've already discerned is a SMES system with these high fields, loose screws become hazardous. The connection point between the superconducting network and the traditional electric network is hazardous for a variety of reasons. And there's obviously other integration challenges. Questions about this? This isn't, okay. All right, so you don't get anything for free. And if you're putting a superconductor on a ship in any form, there's going to be a set of challenges associated with that. You have to put cryogenics on the ship, and the Navy commissioned a study on that already with Dr. Ian McNabb from Post-Naval Graduate School. So folks that are want to talk to him, I recommend or point you in that direction to speak to him. He has a report that is restricted that talks about the challenges with putting a cryogenic on a ship and what that would be required. There's also the integration challenge of just making the unit fit in the space and electrical system that it has to fit in. And contractors aren't necessarily going to know that.
For customer service, press 3. For the deli bakery, press 4. For the new...
I'm going to keep going. And then there's demonstrating unique military specifications. So shock and vibe. There's training staff to use these things. There's finding parts when it breaks. Can't just go to Home Depot and buy a superconductor right now. And there's making the connection points safe and making the whole system safe. But the point I want to make here is that these are logistical engineering design challenges. They're not scientific barriers, mostly. So it's not a question of is it physically possible, it's a question of all these other related issues that the military can deal with much better than having a fundamental physics limit. Okay?
So Matt, I'm going to stop you here for a second.
Go ahead.
So you were talking about the challenges with hardware on a ship-based system. Would that be applicable to any sort of mobile system, or is it just of concern when it's operating and in movement? Like, so could you deploy a magnetic energy storage or an HTS to a remote operating base or something like that and then set it up? Or would you have those same concerns?
Well, in theory, yes, you need to have a supply chain for the cryogenics. You need to have replacement parts for the cryo cooler or duplicate cryo cooler system set up. You need to design it correctly. So good example is a diesel generator. So would a diesel generator be that much better if the generator itself was superconducting versus conventional? And so that question has probably already been looked at by the Army or the Navy for sure, because superconducting is not new to the military. But the question now is, okay, that was maybe the generator in 2010. What does the generator look like in 2025 if you include all the patented innovations from Tokamak Energy and Commonwealth? And Commonwealth and Tokamak Energy supply the magnet to, say, a partner like GE to fabricate the generator and then put it in a demonstration platform that you can go out and just test it. So that's sort of where I think we should go next. I don't know if that answers your question.
No, it does. Thank you.
Okay. So the application space is enormous. Ship degaussing has been the first thing that was deployed. And that is basically just a cable that runs along the ship, essentially. And that is now out on a Navy platform right now, which is exciting because that's the first thing that's gotten out there. Ship motors for all electric ships. I mentioned the Florida State one and the Philadelphia one. There was also one developed by General Electric. There was one developed by General Atomics. And I'm sure there's been more in the open literature space. And again, the question is, okay, if you put a plot of performance for all these ship motors, if you add in the coolant channel, the whole magnet design, the no insulation coils, and the other innovations from fusion, how much better is the ship motor now than it was 5 or 10 years ago? It's an open question, I think. Superconducting engines for aircraft. There's been a lot of work on that for the all-electric plane. I think the all-electric plane is something that the DoD isn't going to jump at yet until the commercial sector really tries it first. And there's been some that have been flown, but it would be interesting to sort of, again, add in these innovations from fusion and see where that technology could go now. There's electrical wire for ships, so superconducting wire on the ship. There's energy storage systems, the SMES system, I talked about, that giant capacitor. There's a diesel generator that could be superconductor. And there's, with SMES, that could act as a power supply for high-powered microwave sources or directed energy lasers. Again, I don't know the application space. This would be really a question for the DoD. But you can help steer all this development with funding, SBIR funding, rapid innovation funding, BAAs or whatever, to help steer industry as fusion companies stand up these businesses towards the applications that you need to solve.
Not really a question. We were talking about the effort to forward deploy one of these energy storage. If the Army is talking about forward deploying small nuclear reactors, small modular reactors, and defending those in whatever forward deployed position they put them, I can't see that supply chain as being any less difficult or really any more difficult than your energy storage device. And they probably complement each other pretty well. If you got a small modular reactor to power a base, but that reactor can't handle peak demand for all of directed energy weapons that are going to have to be in place to defend against swarms of drones or other types of systems, I could see them complementing each other very well. It was just more of a thought than a specific question. The technologies I don't think have that much overlap because cryo is low temp and small modular reactors are high temp.
Yeah, I mean, everybody would love these magnets to work at high temperature, so they'd love them to work with nitrogen. The reality is that the colder you go, the better performance you get. So you could go to nitrogen, but you lose something in performance, and that's a trade-off you have to make. But that's not a very good answer, because if you wanted to dig into the design system, you can probably find lots of innovations and ways to pick up performance through better design of magnets, better design of the whole energy storage system. SMES is not new. It was tried at NWSC. I believe it was Code 88, but the person to speak to is Peter Cho. He worked at the Naval Surface Warfare Center. He worked on a SMES demonstration in the 90s, and he can talk about the challenges they had then. And SMES was also, there was a work done in Japan by the Tokyo Railway Company. They developed a SMES unit to push these maglev trains, and that system was designed by Livermore in the 90s. So there's a body of work here that you can pull from, and then you pull the patented innovations from Tokamak Energy and CFS, put the two together, and you could do a design study to see where the technology is now. In fact, that's sort of my last slide here. Other people have made this point, and I'm just going to repeat something that someone else told me to say here, which is that, okay, wire prices right now are still very high, but they're dropping. And I think they're going to continue to drop as fusion demands more wire. They're going to force the supplier base to step up production. So the cost is going to come down somewhat, we hope, we think, and the availability is going to proliferate, and the quality of wire is going to proliferate. So you can get them in longer lengths than 500 to 600 meter sections. Heavy prototyping might not be the right move right now, but what the DoD can do, or the Navy can do, is design studies. Take a piece of software, build an entire CAD model of this system, put it through its paces, and see how good the system could be, and figure out the best way to design these systems. So what the Navy could do is a generic motor, a generic generator, a generic power supply, a generic power conditioning system, or a generic all-electric grid. Make a design of that on the computer, simulate it, and figure out what the best design is. So in a couple of years, when the wire price does come down, you're ready. That's what I think needs to happen now. So there's, as I said earlier, there's been lots of models done in the open literature, but a couple of things are missing. One, there isn't a universal design. There's a lot of variability. So there's not really clarity on what the best motor, superconducting motor, looks like. There's a lack of economic analysis. Essentially, none of these papers, they're science papers. They don't really tie into if the wire price is $80 a meter versus 60 versus 40 versus 20 versus $10, what designs become economically possible as the price comes down? That's something that I don't know as they've really looked at in the open science literature for designing these systems. And then most of the papers are sort of ignorant of what's happening inside the companies, the fusion startups like Tokamak Energy and Commonwealth. So pulling those innovations and putting them in this design is really what needs to happen too. So it's an idea sort of pullover or transfer. Questions?
So Jeremy, Ryan, Tom, you guys have been in the chat. You want to bring that out into a verbal conversation, please?
Yes, I can start. So one of the things is just the talking about the magnetic imprint and the stray fields. This is a problem in a lot of areas, and at the spallation neutron source, they're talking about putting a high field magnet in in a beam line and they're worried about it affecting the equipment nearby. Like, for example, if you have a pump that is in a straight field, the pump can wear out a lot more quickly because you're getting this magnetic force on it. And for superconducting magnetic energy storage, usually you like to have a lot of energy, and that's stored in the magnetic field, which is just the integral of the magnetic field over all of space. So you want to have, you're going to have a lot of magnetic field around it. On a ship, I'm not a military guy, but I would expect space is at a premium. And so now you have to worry about all of that. Now, compared to land, where even if it's a remote operation location, you probably have a lot of land where you could put your SMES device away from everything else.
Is a really good point. Anything else, Eugene? Other points, questions, comments?
So yeah, just a couple here. So Jeremy and Ryan, I mean, you're both familiar with the forum, and I listening to Tom, listening to Matt, there may be some benefit, and definitely this would cross enough sciences and industries to possibly create a forum that is focused on fusion, SMES, and HTS, because you're looking at shielding, and I'm sure there's composites out there that can help with that. I'm sure there are construction things out there that would help with loose hardware and stuff like that in those, containing the magnetic fields, all that kind of stuff. And here is the challenge with innovation. And this is the challenge that this platform is trying to overcome. Innovation is stovepiped. Most of the people on this call today are involved in energy or in fusion specifically, and that's great, but we have tunnel vision, and we don't want tunnel vision. We need to bring in the people from the composites industry to listen to our challenges and to help us solve those challenges, because we're not experts in those fields. And and I know, Matt, you've been working on it for a while, trying to build some kind of a consortium that is addressing these issues, and some of the things that we've talked about in these consortiums is to identify a place to start. I worked with a guy at the Pentagon, Joe Rouge. I'm sure anybody here from AFRL might be familiar with Joe Rouge, but I always loved his philosophy. His philosophy was, I don't want to spend 6 years modeling on a computer. I understand we have to do some modeling on a computer, but let's go build it. Let's test it. Let's break it. Let's fix it. And we'll get there faster that way. And I think that's the thing. I mean, we talked about this with the directed energy people at Dahlgren, and they liked the idea, and it came down to a funding issue, is what if we came up with a dual use SMES, where we could power ship systems or power base systems, and then when a threat warranted it, we could disconnect from those systems and dedicate that to the power source. Because right now the power, or dedicate that to the directed energy weapon, because right now the power for the directed energy weapon on these ships at these facilities is dedicated only to that. And it's a waste. It's a waste of space. It's a waste of energy, and it gets used once a month for a test or once a week for a test, and the rest of the time it just sits there idle. So these are the kind of innovations that we need to identify. These are the kind of solutions that we need to try and come up with. So so Jeremy, Ryan, I'd like to talk to you guys. If there's anyone on here from Sandia, anyone on here from AFRL. My guess is that you guys are further along on this path than Army or Navy, and let's get you involved in this consortium that Matt is trying to bring together, and let's see if we can't bring in all those pieces and parts and solve some of these challenges. So I'll get off my soapbox now. Sorry, Matt.
No, it's okay. Other comments, other thoughts?
You know, I think that's a great idea, Eugene. And the place you would start, in my opinion, is the requirements for both of those, and then start brainstorming how you can make one system to meet both of those requirements. And your point on, you know, don't model stuff for 10 years is a great one. In the academic area, we tend to do that before we build these big systems because they're very expensive. And then I've been working with some startup companies, and they're at the other end of the spectrum where they're just building stuff, and you know that it's not going to work, and they're just like a pedal to the metal. Let's do it anyway. So it has to be some you know, optimum point, if you can find it, where you're testing stuff, you're learning. You got a lot of certainty after you do a test of what works and what doesn't. But going back and forth with the modeling.
Thank you, Tom.
Yeah.
I want to acknowledge that there are people on this call that should be up here talking rather than me. Tom is one of those people, because you guys know more about this topic than I do. Again, I'm a fusion guy. That's really
I don't know about that, Matt. I've liked what I've seen so far. I've already learned some things.
Okay. All right. Well, anyway, I'm going to wrap up here.
But you have plenty of time, so I want to open it up. Does anybody else? I mean, I know there should be people here from AFRL. There were a lot of responses from AFRL people. Please chime in. Go ahead, sir.
Hey, this is John Liggins-Land from AFRL. There are certainly groups that would love to participate in trying to get information and building a consortium on this. They are mainly in Dayton, Ohio. But Matt, I can introduce you to those folks and have the discussion. I think one of the things that's interesting is that the little bit that I know is they're facing many of the topics that have come up today. How long does it last? How do you control the magnetic field so it doesn't mess with something else? There are even people talking about how you might try and get this on space platforms, which are very compact and very worried about magnetic fields. So just I'm happy to work with the team to help bring those people that are better experts than I am to the fight.
Yeah, because I do know that NASA is looking at this as a solution for extraterrestrial colonization and, you know, mining and things like that, because you could take this. You could put it on the dark side of the moon where it's nice and cool most of the time, or put it in a cave or something like that where it's far enough away from people and it has a natural cryo cooler around it.
Yep. Yeah, absolutely. And of course, I mean, you know, the really exciting thing right now, the U.S. Space Force has come out and noted that we need to work with partners that are developing commercial partners that are developing the economics of space. And so the distinction of a military platform and a commercial platform, they need to interoperate almost assuredly. And so that offers some opportunity for both commercial and defense people to play together, specifically on high temperature conductivity, superconductivity.
Yeah, thank you. Yeah, and I know I've had some composite people present on the forum and others that I've talked to, and there are some fantastic composites out there that are, you know, 99.9% conductive, and you can dope them to stop gamma radiation and things like that. So I'm sure we could stop magnetic fields as well.
Yep, absolutely. Just, you know, it's all a question of size, weight, and power.
Yeah, exactly.
Yep.
Okay.
All right. Anyone else want to chime in? Anyone from university that wants to talk? Love to hear from you. All right.
Well, then this is my last slide. So more resources. Michael Ginsberg is up next. So I'm hoping he fills in a lot of questions that have already come up. So I'm queuing you up, Michael, for your presentation. Commercialized fusion technologies have only sort of emerged a little bit. TAE has stood up a division that has a power solutions group that's really interesting. So just a little digression, TAE developed this big machine called Norman, and it's a 750 megawatt fusion reactor. And they had to supply power from a grid that only gave them 2 megawatts. So they had to develop a whole bunch of energy storage, power electronics, so switches, and compact systems for supplying power to their fusion device. And now they've turned around and commercialized that. And they have a business where called Power Solutions for fast EV charging, for energy management, for cell control. It's really exciting stuff, and it may be good. Maybe we could have them on the forum to have them talk about what they're selling. There's also Tokamak Energy. They're up next, as I mentioned. If you want to have internal discussions, the two folks for superconductors that I know that are good is Scott Coombe at Office of Naval Research and Mr. Peter Ferrara, who is the team lead for the Applied Superconductivity Office at NWSC Philadelphia, or NSWC Philadelphia. There's also Dr. Ian McNabb, which I referenced his report. He got commissioned a few years ago to write a report about the challenges of putting a cryogenics on a ship. And that report is restricted at CUI. I can't see it, but you can see it. And then, of course, the gurus for this are the Center for Advanced Power Systems, the CAPS Center at Florida State. They've done a lot of work in the all-electric ship world around power control, hardware, power monitoring, and software for a superconducting grid. Finally, we have two white papers. One of them is done. One of them is still being worked on. But if you want a copy of that, please email me. The first white paper looks at fusion generally, so not superconductors, but fusion as a whole, and looks at a variety of different technologies coming out of fusion, from lasers to power control to superconductors. And it has some recommendations. In fact, there's a nice long list of SBIR topics in that paper if you want to craft some SBIR programs. And then we're drilling down on superconductors specifically, and we're working on a paper right now on that. And then lastly, if you want to learn more about fusion, I have a book. It's on Amazon. You can buy it. And I have this fusion masterclass on YouTube, which is great. I recommend that highly. 12 lectures on fusion, 30 to 45 minutes a lecture. You can listen in your car while you're working out, while you're going for a run, while you're cooking. Fusion explained for normal people in plain English. So I highly recommend that masterclass, and it's free. That's it. Any questions? Any other questions?
No, we got some things in the chat here that I want to bring out. I also want to say, is that the book that I read, Matt?
Probably. It's
okay. Yeah. No, it's a great book, especially for people who know absolutely nothing about fusion. And I really enjoyed it. It's kind of like a dummies book. But yeah, no, I appreciate that. So Aaron Washington put a statement in here, and Aaron, I'm going to ask you if you wouldn't mind put your email in the chat as well. Matt, if you could put your email in the chat. Tom Painter as well, please put your email in the chat so people have it. So we can.
Dr. Washington is from Tokamak Energy, and whatever he said, I defer to him.
Okay.
He knows more about his company than I do. So
okay, he was talking about NASA, so
okay,
I wasn't sure if he was with NASA or the federal government. And then Greg Brittles.
Dr. Greg Brittles is from Tokamak Energy as well. So if he's on the call, he can speak up.
Hi, I'm online. I'm online and keen to contribute.
Okay. So do you want to say anything now, or do you want to wait until Michael's going?
Well, yeah. I mean, I guess just one kind of nice comment picking up on what Matt had said earlier. I can put my camera on. I am here in real life. Hello. So yeah, with things like superconducting motors, for example, that one of the key benefits is reduced size and reduced weight. So the efficiency of a superconducting motor might only be modestly better than a conventional motor. Typically 1% might be a value for the increased efficiency. Even that adds up, by the way, if you're running a very powerful system. So that's 1% isn't to be sniffed at. But the significantly reduced footprint and weight is what really matters for applications like if you want to put the speed, for example. That's huge benefit. Yeah,
all right.
That's what I wanted to say. Yep.
Okay.
More to follow in Michael's talk, and I'm around to help answer any specific magnety questions.
Sounds good. And then Aaron, did you want to comment as well?
Hey everyone. So the comment about the NASA was from my experience with the Department of Energy before Tokamak, but I know we were having conversations that they were looking into, as you mentioned, superconducting materials for the moon for exploration. And so that was 6 years ago when I had that conversation. So I'm not sure where they are today. But that's definitely, I just wanted to validate what you were saying.
Okay.
Okay, Eugene, I'm done. So I'm gonna
Okay.
turn off my mic and let the next presenter go.
All right. So then, so through this transition here, I want to, a lot of people have checked in. I'm going to ask you that there is no requirement to put your email in when you register. I see a lot of names here that I don't recognize. So I'm guessing you got forwarded invitations. If you want to stay in communication, if you commented and you want me to set you up with direct contact with people on here, please put your email in the chat so that I have that. So when I do the follow-up after this, I can actually connect you to the people that can help.